Hello, kiddos. This is Mr. Gilmore with the 2.1 Geometrical Postulates lesson. So now that we're out of chapter 1, where we have pointed at our objects and we've given these objects a term name and a definition, we now begin to look more along the lines of choices that we're going to be making in our system called postulates. Postulates, we've discussed this a little bit in class already, but postulates kind of have these 4 dimensions to them. The first dimension, first of all, is that it's a choice. It's something we're choosing to be true, something we're saying it's true, and we're sticking with that truth. To add into our system. And of course, when we make decisions to add these truths into our system, to choose them into our system, there will be consequences to it. Not necessarily they're going to be good or bad consequences, but just that there will be consequences that follow from our decisions. Second thing that postulates have with them is that these are additional properties. These are properties that we are choosing to give to our objects. So that means these properties are not inherent to the object already. This is something that is being given to the object, which we'll look at several today, in which we are handing the object this property. And we've already seen some geometrical postulates in nature, which you'll see in this lesson is a bit redundant, but just to make sure that we're understanding that this kind of captures the heart of these choices being made. The third thing that postulates should be is they should be obvious, right? These should be kind of well duh moments of this is self-evident to me. Like this has to be true just because it's true, and you don't have to convince me otherwise. And then the last kind of dimension the postulate should have, it should be fruitful. You need to be able to produce stuff from this postulate. You don't just want to make statements of truth and then just they don't get used at all. So these statements that we're going to be making in today's lesson, we're going to be doing one of two things. We're going to introduce a set of postulates of geometrical nature, which you'll see and recognize a few of these. And then what we're going to be looking at is practicing what's called inferencing, where we're going to be drawing truth, something guaranteed true, from a given statement. All right, so let's jump into this. So, first of all, what is a postulate, right? A postulate, we can say, is a basic self-evident assumption. This is a choice, again, that we're making to add into our system to say this is true, and we don't have to argue that this is that it's not true. Basically, that there's no evidence we need to say that it is true. That we have to guarantee it's true. It's just a truth that we know it is true because it is. And again. Because of the choices, we are going to see that these postulates are going to be fruitful in nature to help produce other inferences, other statements that are being made that we know absolutely are going to be true along the way. So we've encountered this postulate already, the line existence postulate, or the LEP, and we know what this one does. We say, hey, look, it's an interaction over objects. It's a truth that we're choosing to be true, and it's really fruitful. We see that through any 2 points there exists a line. And remember, when we say that line passes through them, that means that those points are on the line, and we also know that this line is to be unique. So that's actually kind of a choice to ourselves by saying that we're choosing that there is one and only one line that passes through point A and point B here, thus giving us that choice in nature, and also it's going to cause some consequences within our system, which we'll talk about later on. Next one is a ruler postulate. We've briefly mentioned this one. I mentioned earlier in one of our previous lessons that it does have 2 clauses. The first clause we already mentioned, which is every segment has a unique positive length. However, there's a second clause. And the second clause, it's a little bit wordy here, but let me kind of sum it up what it's saying. It's basically saying that because we have a ruler postulate, we can make measure. So say, for example, we're given a line and some point on that line. Then I want to make a measure of some positive real number. We'll call that positive real number R. That means there exists really 2 points, an X and a Y, that are on that line, such that on one side of P, we can measure out a length of R, and on the other side of P, we can measure out also that same length of R, such that we get 2 identical measures, Px equals Py, which is actually then equal to that positive chosen real number. So to illustrate this, let's say that we have this line L, point P on it, and I chose our length to be a length of 3, that I want to measure out a length. Well, I actually have, because of this line that exists there, I have 2 options. I can actually build that segment of length 3 in two directions, on one side of P and then on the other side of P. So you see there's a value of X, or sorry, a point X and a point Y, such that PX and PY are equal, because they both measure 3, and it's equal to that already chosen real number. So clause 2 of our ruler postulate says that we can make measure. So we have our first clause that says measure, right, that has measure to it, and then we can also make measure. So, what does that ruler postulate then allow us to do? It allows us to say that we can actually begin adding measures together. And here's another really obvious property. It's called the segment addition postulate. And also notice then, in the parentheses in the title, I just have SAP. You could definitely shorten that up to SAP in the future. If you see a postulate that does not have that, it doesn't have a shortened acronym, then do not shorten that postulate, please. Leave it just as it is, because we don't want to call this, you shorten it up and it be confused with another postulate. So let's jump into this one. It says this, that if point C lies on a segment AB between points A and B, then the length of segment AC and plus the length of segment CB is equal to the entire length of segment AB. That should be pretty obvious, because down below we kind of visualize placing some point C in between A and B, which then divides it into two subsegments. Well, each of those subsegments have measure. We can then add the measures of those subsegments together, and it equals the whole. So essentially, you could think of this generally by saying the sum of the parts equals the whole. The sum of the parts equals the whole. Let's talk about the straight angle. The straight angle is one of those in which we give a property of measure to. We give a property of that measure of 180 degrees, right? 180 degrees. We're actually saying that all straight angles measure 180 and only straight angles measure 180. So again, we note that this does not say anything about the definition of straight angle, because in the definition of straight angle, we already know the inherent property is just saying that two sides form a line, right? The two sides of the angle form a line. But when we give it that property of measure, that's going to be under this something different. That's going to be under the straight angle postulate. And notice we're not simplifying this one to call it SAP, because we already have an SAP. That's a segment addition postulate. So when you give this property of 180 degrees to your angle or straight angle, that's not by definition. It is by postulate. It's a choice. We're choosing to give that property over to our straight angle. So please be careful that if I were to ask you what the definition of straight angle is, you are to write an angle whose sides form a line. No more, no less. Do not include the measure of 180 degrees in the definition. But if I said, hey, what's the measure of a straight angle, you could say 180 degrees. And if I said why, you would say, oh, that's by postulate. That's a choice we've made to give that property to our object. This also leads us then into the protractor postulate, right? We've stated that every angle has a measure between 0 and 360. That was mentioned in a previous lesson. But for clause 2, this is just like our ruler postulate clause 2, we can make measure. So let's say we are given a ray and some positive real measure that's between 0 and 180. Okay, we could make that from 0 to 360, but we just want to stick with making an angle between 0 and 180. That's all we're going to need. Then what we're allowed to do then is we can actually produce two rays from the two rays that are coterminal, meaning they have the same vertex as our original ray, such that it measures out the chosen degree measure that we want, right? So we actually have possibility of measuring kind of in two directions like we did with the segments. We can measure in two directions, kind of a clockwise or counterclockwise direction. So let's say I'm giving you this ray AB, and I want off of this ray AB to create a measure of 30 degrees. Well, that means I can rotate counterclockwise or clockwise, and I'm able to produce that angle measure of 30 degrees using my protractor postulate's second clause, the ability to make measure. So whenever you encounter the ruler postulate and protractor postulate, think of its two clauses. You can measure and you can make measure with it. And of course, with that, then we have the angle addition postulate, or AAP. Notice we do have an acronym for that one, right? The shortened up acronym. So before we split, all right, so when we split a segment into subsegments, we can now split an angle into subangles. So let's say we have an angle, given angle with ABP or ABC, with a point P that lies on the interior of that angle. There's a ray that we can produce there from the same vertex as angle B or angle ABC, and that ray divides our angle into two subangles. Well, I know that each of those subangles have measure. I can add those two subangle measures together to give me the whole. So the measure of angle ABP is equal to the measure of angle ABP plus the measure of angle PBC is equal to the measure of the whole angle ABC. Again, tapping into that generality of the sum of the parts equals the whole. That should be pretty obvious. Now, what are we going to do with these postulates? Well, we're going to partner them up with our already given truths of definitions. Definitions are true, and we have chosen our postulates to also be true. And we call these guys the engines of inference. Later on, when we add theorems to our list, we'll also be able to use previously proven theorems as these engines to make inferences of. What is an inference then? An inference really is a joining of two statements such that the second statement genuinely follows the first statement. When I use that term follows, what I mean by that is that the given statement, statement one, there's something that I can draw a fact from, that there is a follow up fact that I can make a statement about, and that follow-up fact that I make a statement about, I can justify that using a definition, a postulate, or a previously proven theorem. And so right now we only have definitions of postulates. Well, we're going to practice some inferencing here now in the next couple slides. What you're going to see is you're going to see two statements. The first statement is something that's given. That's just something that we're already just going to have. Okay. And then what you're going to see is we're going to make an inferencing statement. There's going to be a second statement that follows. And what we want then to do is check to see, does the second statement genuinely follow the first? How do we do that? We need to be able to justifiably support that second statement being drawn by either a definition, a postulate, or a theorem. Now, it's only going to be definitions, postulates today. Okay, so let's practice this. You're going to see again a statement being made, and then we're going to draw a truth from it, and we'll know it's guaranteed truth whenever I can justify it. But if I cannot justify it with a definition or postulate, or I know it's not going to be 100% true of an inference, then that's a non-genuine inference. I cannot actually make that ultimate conclusion because I don't have the evidence to support it. So let's practice this. So here we go. In the italicized sentence below, that's where we see the first sentence, which is going to be our statement being made. And there's going to be then a second statement that follows the word thus. That second statement is our inference. So let's ask these questions initially, and then we'll practice this with those italicized sentences below. It says this: do we have a genuine inference below? That is, does the second statement follow from the first? If so, by what definition or postulate? So we're going to be saying it does follow or it does not follow. And if it does follow, we have to justify with a definition or postulate. And if it doesn't follow, we got to explain why we do not have enough evidence or why there is no definition or postulate to support our claim. So let's take a look at the two statements. The first statement is already given. That's the first sentence. It says points F and G are given. Okay, so I've handed you 2 points F and G. Let's make an inference. Thus, a unique line exists that passes through them. Does the second statement, does or does not the second statement follow from the first? Well, in this case, it does follow. Why? We're able to justify that with the line existence postulate. Through any 2 points, there exists a unique line that passes through them. So there we have it. I made a proper inference in my second statement. Okay. Now, what you kind of see going on is I've already kind of preloaded what the given statement is and what the inference is, right? I've kind of already preloaded that. So there's going to come a day when I'm going to give you a statement and you're going to have to draw out the inference on your own, which means you're going to have to not only draw out the second statement, you're also going to have to justify that second statement and make sure that you are creating a genuine, true inference following from the first. This is just kind of a taste of what inferencing looks like and how we justify it. So what you're going to help me practice with in this chapter is really just making sure that the inferences that I have are true by justifying them with a definition or postulate. Let's practice this again. So again, same questions as before, but now we have new statement and a new inference being made. Here's our new statement. Angle 1 is right. So that's something given. Thus, here's our inference. Angle 1 measures 90. Let's think about that. If I give you an angle that's right, does it then make sense for me to inference that it measures 90 degrees? Well, of course it does. It follows. Yeah. Why? By the definition of a right angle. Right angle definition says that if you have a right angle, it measures 90 degrees. Okay, so it is a true inference. It is genuine. I'm able to support it, right? But once again, what you're seeing is already a preloaded inference being made of I've give you the statement and I've already made an inference. But again, in the future, I'm going to give you statements, and you're going to have to make the inferences on your own. Let's do a third one here. So again, same questions as above, different statements below. Angles 1 and 2 form a linear pair. Thus, angle 1, so this is my inference, thus angles 1 and 2 are both right. Does that second statement genuinely follow from the first? That if I hand you two angles that form a linear pair, now that's all you know about them, is the only thing that's given about them is they form a linear pair. Does it then follow that both have to be right angles? No, it does not follow. Nowhere in the definition of linear pairs does it say anything about angle 1 and angle 2 needing to be right angles. They can actually be any pair of angles as long as they are adjacent and their non-common sides form a line. So they don't necessarily need to be right. That is an improper inference. That inference, now, here's the thing. Could that inference be true? Yes, it could be. But it has to be true 100% of the time. Is it true 100% of the time? No. So it's not a proper inference. I actually am not able to justify that any way, shape, or form. So that is not a proper inference. That is not a genuine inference. And again, I kind of preloaded this as saying, here's a statement, and I already generated a wrong inference intentionally so you can see and kind of get the feel of what that looks like and what to avoid, right? I cannot make that second inference. So that means I go back to my first. Now, let's say I fix this. Let's say I said angle 1 and angle 2 form a linear pair. And then I said this, thus, angles 1 and 2 are adjacent. Then you could definitely say, yes, it does follow because from the definition of linear pair, we know that the angles have to be adjacent. So that is something that I can make a proper inference or a genuine inference of. Here's one more, or an additional one. We got a couple more. I got a couple more slides here. So let's say I make the inference of this, or make sure I make this statement. B is the midpoint of segment AC. So I hand you a segment AC, and I tell you that B is the midpoint on it. Thus, the measure of segment AB is equal to the measure of segment CB. Is that true? Well, let's unpack our definition of midpoint. What do we know about it? Well, midpoint means that the point is on the segment and it divides it into two equal subsegments. So is our inference true? Yes, our inference does follow because in the definition of midpoint, it tells us that it divides that segment directly in half, which means we get our equal segments from that. AB is equal to CB. So yes, that is a genuine inference because I can draw that directly from my definition of midpoint. Let's look at our one more. This last one's a bit of a tricky one. So first statement is this, and you'll notice what I did was actually just reverse my first and second statement from the last slide. So let's see if this is a proper inference. So my first statement is AB is equal to CB. Thus, B is the midpoint of segment AC. Well, let's take a look at our first statement. All I'm telling you here is that I have two segments that are equal in measure. A segment AB is equal to segment CB. Now, do they share point B? Yep, they do share point B. So then is it okay for me to say that B is the midpoint of segment AC? Well, does it follow? No, it does not. Why? Because nowhere in our first statement did we ever mention the location of point B. Is point B on the segment? I have no idea. All I know is that point B is, yes, being shared by the two segments, but does that mean that A, B, and C are collinear? Are they all on the same line? I have no idea because there's a possibility that we actually end up getting two segments that look like this. Here's a segment AB, so I'll mark that that's A. Here's B, there's C. If I were to tell you again, AB is equal to BC, that's my first statement. That we know to be true. But is B actually on the same segment as AC? No clue. If I actually made that a triangle, right, we have no idea. In this case, that would be a hard no. B's not on it because it's not on the same side as AC. Well, is it possible B is the midpoint? Yes. But remember, inferencing has to be 100% correct every single time when you make an inference. So in this case, this does not follow. I cannot actually make this proper inference. So if I said AB is equal to CB, is there some other inference I can make that I could actually remedy this? That could be a little trickier here. I'm not actually sure what inference I'd actually be able to draw from this because, again, I would need some more information. I don't know where point A, point B, and point C are, other than that I know that I have two segments of equal measure. That's all I know. Maybe I can make a proper inference like this. If AB is equal to CB, so that's my first statement, AB is equal to CB. Thus, that means I could use hash marks on my segment AB and CB. Yes, that would be a proper inference. I could put hash marks on those segments and to denote the equality between them. So that may be a proper inference. But in the long game, we are going to be looking at actually drawing inferences on our own. I've given you these already. You're going to help me this chapter, though. Practice giving me proper inferencing. So we'll continue this in the next lesson, looking at some other postulates, practicing other inferencing, and then we're going to be looking at what are called chained inferences, meaning drawing one inference from one statement and an inference from that inference, and then an inference of following those inferences, and we are able to chain inferences together into what we call an implication table. So we'll be looking at that later in this chapter. All right, that comes to the end of our first lesson here, 2.1. Please be sure to work on that 2.1 homework assignment. If you do have any questions, do not hesitate to email me. With that, be good and do good.